Why hello lovely humans, Jen Foxbot here. Welcome back to another super cool edition of Math Mondays. We gonna do some math today. Hey! Okay, so in this video, we're gonna talk about the Heisenberg Uncertainty Principle. Huzzah! I'm really happy someone asked me about this right after I did the video on accuracy and uncertainties, because there's a lot of misconceptions about Heisenberg's uncertainty principle. Heisenberg's uncertainty principle looks like this. The uncertainty in position, x, times the uncertainty in momentum, p, must be greater than or equal to h bar over 2. H bar is Planck's constant divided by 2 pi. Planck's constant is a well-known constant of the universe. It is a very, very, very tiny number. So Heisenberg's uncertainty principle is applicable when we're doing problems in quantum mechanics. Because most of the time in our day-to-day life, we're never going to run up on this limit. And again, it's not a limit of our ability to make measurements. It's a limit of how much we can know about the universe because of the wave nature of reality. And so when we're dealing with throwing a baseball, we are way above this limit. Don't need to worry about it. We can talk about the position and the momentum using projectile motion to predict the path of a baseball. No problem. But as soon as we're on these teeny tiny subatomic scales, then all of a sudden things get really weird because particles act as both particles and waves. This is called wave-particle duality. And so waves are a little bit different than particles, right? Like, it's weird to talk about a point on an ocean wave, because ocean waves spread out, sound waves spread out, light waves spread out, and likewise, matter on a quantum mechanics scale spreads out. In quantum mechanics, it's a little different though, because a sound wave, when we're talking about what is waving, well, that's easy. It's the air. With a water wave, it's the water molecules. With light, it's electro and magnetic waves. But when we're talking about matter waves, what we're actually talking about is the probability that's waving. And that's a little weird. Totally get it. This is why people get to quantum mechanics and they're like, what is going on? Oh my gosh. But that's also why quantum mechanics is super cool, is because it totally flips our idea, our intuition on its head. And so Heisenberg's uncertainty principle basically tells us that because nature is both a wave and a particle, we can only know so much information about a given particle at a time. Why is that? Well, to really understand this, we really need to understand wave theory, and that is a whole nother subject that can get very complicated. And to keep this video under an hour or whatever, to a reasonable time limit, I'm not going to dive into wave theory all that much, but what I did want to show you was basically where Heisenberg's uncertainty principle comes from and why it exists. And again, it's not a limit in our ability to make measurements on quantum systems. We can be super accurate. It's pretty impressive with the tools that physicists have developed. They can be super accurate about position and measurement. But because particles are waves, we just can't know everything about them. So one trick that folks do in audio engineering, if we want to get a digital signal, which is either on or off, if we want to get a digital signal to represent a sound wave, we have to do a few mathematical tricks. So what folks do is use what's called a Fourier series, which basically combines different types of waves to get a different type of waveform. The more waves that you add with different wavelengths and different frequencies, the more accurate you can get your resultant wave. And so if you want to get a very narrow wave packet, you add a bunch of waves together with different wavelengths. The more waves you add together, the more accurate your wave packet is going to be. So you would add, oh my gosh, all of these, and then you get a wave that is more representative of the sound wave that you're trying to get to. The exact same thing is done in quantum mechanics. Because particles are localized, which basically means they are constrained in time and space. For example, if you have an atom and then you have the quantum mechanical electron waves surrounding that atom, the particle is localized, or the electron is localized in that orbit. And so instead of like your standard sine wave, I'm running out of space on the board. Instead of your standard sine wave, which looks like this, a particle looks more like a wave packet, which is like this. And so we want to add many waves together to get a representative mathematical model that is accurately depicting what the experimentalists have discovered. That's really the trick in physics is there's this play between theory and experiment. Sometimes it goes both ways, but they both have to match, meaning the theory, the equations must match reality. Because we're talking about physics. Y'all pure mathematicians can go and do whatever you want. There's almost no rules, almost. But in physics, we are very constrained by the rules of nature. And so all of our equations that we use in physics must accurately depict the nature that the experimentalists have very carefully measured. And so, in quantum mechanics, particles are represented with the Schrödinger wave equation as wave packets. And so because they are localized, you have to add a bunch of waves together to get this wave packet. So if I were to break this up, it might look like something like this. I don't know, whatever. I'm getting a little lazy. So, like I said, the more waves you add together, the more accurate your wave packet will be. So, you could think about this as the uncertainty in position. Whoops, delta x. So as your uncertainty in position gets more and more narrow, as your wave packet becomes more and more precise, the more waves that you have to add increases. And it gets really big. And all of these waves have different momenta. So then all of a sudden you're trying to quantify this particle, and you're like, oh, right, my uncertainty in position is super small. Heck yeah. Oh, but I have all of these waves, and now all of a sudden, when I'm trying to quantify the momentum of this wave, well, foo. So the more accurate your uncertainty in position is, or the smaller the uncertainty in position is, as delta x goes down, the uncertainty in momentum must go up because this relationship must be held. What does that look like in practice? Well, let's say we are able to accurately measure the position of a quantum mechanical particle, like an electron, and the uncertainty in its position is something like 1 times 10 to the negative 34 meters. Then we can calculate the minimum uncertainty in our momentum using this constraint. So we would solve that by saying delta P is greater than or equal to h bar over 2 divided by the uncertainty in position. And since this equation is going to be a pain to do in my head, I'm going to use my handy dandy calculator. So let's again remember h bar is Planck's constant, which is 6.62 times 10 to the negative 34th divided by 2 pi. That is h bar, and that equals 1.05 times 10 to the negative 31st at that bottom line over there. I was double checking my work before I started. And then you divide that by 2, and you get 5.27 times 10 to the negative 35th. And then you divide that by what we said our uncertainty in position is. So 1 times 10 to the negative 34th. And so we get the minimum uncertainty. The minimum uncertainty in momentum must be greater than or equal to 0.526. That's a terrible 5. There we go. Maybe. Huh. Okay. And since we're dealing with physics, we also have units, which would be meters per second. Meters squared per second. Cool. So that seems like a fairly reasonable number, right? But remember, we're on the order of 10 to the minus 34th. That's crazy tiny. So to say that the uncertainty in momentum is 0.526 meters squared per second, that's actually really big. So that's kind of the game that we're playing when we're dealing with quantum mechanics, where particles act as both a particle and a wave. We just can't know everything about them because they are waves. They're spread out over space and time, and the more accurately we try to trick the particle into measuring, the less we can know about another quantity on that particle. So yep, there you go. So that is Heisenberg's uncertainty principle. We don't really have to deal with it in everyday life, but when you start talking about and making measurements on quantum mechanics systems, then you are going to be constrained in how much you can know about that system. All right, so please let me know if you have any questions about this, or if you'd like me to talk more about the wave theory. Or in general, if you have mathematics questions or particular subjects that you're curious about, that's what this is here for. So, leave those questions and comments in the comment section below, and we'll see you next time. All right, bye!